Alright, Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone that is watching this video. Okay, so today I will give you guys a brief introduction about finite control volume analysis, impact of a jet, which is actually part of the experiment for a fluid mechanic one. And the reason I am doing this is because our description of problem and our coding itself is actually related to this topic. So hopefully you guys can understand the description of problem better after I have give you guys a brief explanation about the finite control volume analysis. Okay, so moving on, and okay, let's get to it. Water turbine are widely used throughout the world to generate power, so this is a well-known fact, right? Okay, but today we will focus on one single water turbine, which is known as Pelton wheel. Okay, so the Pelton wheel actually works by a jet of water which is tangentially directed to the buckets over here, as you can see. And because of the impact of water on the bucket, it will generate torque, and that torque will cause the rim to rotate and then develop power. So this concept is relatively simple, but it is very useful for us to generate power, right? Okay. Okay, as you can see over here, these are two examples of a Pelton wheel. Okay, this one have two sources for water jet, one over here and one over here, but this Pelton wheel only have one, but their concept is still the same. Alright, so to predict the output of a Pelton wheel and to determine its optimal rotational speed, we need to understand two things. The first is how deflection of water jet generates force on the bucket, and the second is how force is related to the rate of momentum flow in jet. Okay, to understand this, a simple lab experiment can be done. So, the objective of this experiment is to assess the different forces exerted by the same water jet on a variety of geometrical different plates. And there are two plates that we will use in this experiment. The first is a flat plate surface, and the second one is hemispherical cup. So as you can see over here, this is the setup of the experiment, and here is how it works. Okay, so we have a water supply from here, and then the water supply will go to the nozzle and then being ejected in the form of water jet. Okay, so the water jet will hit the vane, and then the vane is actually connected to the lever over here. And as the water hit the vanes, the water have force, right? They have momentum and it has force. So the force of the water will push the vane and it will push the lever upward. So to counteract that force, the jockey weight will be moved or slide to the right, so that the weight of the jockey weight can balance back the force of the water and return the lever back to its original position. And the distance in which the jockey weight is being moved is denoted as y. Okay, so the experiment was done up to 7 readings, in which the recorded data is for quantity, the time, and y, as I've said before, is the distance in which the jockey weight was moved. So from this value, we need to calculate the mass flow rate, which is m dot. U1 is the velocity of water when it exits the nozzle. U null or U0 is the velocity of water when it hits the vane or the plate. J is the momentum flow of jet at impact, and F is the force on the vane or the plate. Okay, so here are some of the data that we know from the experiment, which is the diameter of the nozzle is 10 mm, and then the distance between the vane and the tip of the jet, tip of the nozzle, is 0.035 meter, and L is the distance between the fulcrum and the center of the vane, which is 0.15 meter, and last but not least, the mass of the jockey weight is 0.6 kilogram. Okay, so from there we already have the diameter, and then the height of vane above the nozzle tip S, and then the distance between center of vane to the pivot of lever L. so we can calculate the cross-sectional area of nozzle. So to calculate the cross-sectional area of nozzle is actually pi over 4 d square. D is the diameter of nozzle, and then we will get this value over here. Okay, so from the mass of the jockey weight, which is 0.6, we can calculate the force of the jockey weight, which is equivalent to 5.89 Newton. Okay, so from there we can calculate the force on the vane, which is actually F1. To do that, we can use the equation of equilibrium of force. F1 d1 equals to F2 d2. F1 is the force due to the water jet hitting the vane that we want to calculate. D1 is L, which is actually equals to 0.150 meter, equals to F2. F2 is the force due to the jockey weight, which is 5.89 that we have calculated earlier, and D2 is the distance in which the jockey weight was moved, which is Y. So if we rearrange this equation, we will get F1 equals to 0.03924 D2, but D2 is Y, so we can replace it with Y over here, so we will get this equation over here. Okay, so to calculate the mass flow rate, which is m dot equals to mass flow of water divided by time, or if we look at the table of result, it is quantity over T, and then we can convert mass flow rate into volumetric flow rate by dividing m dot divided by density of water. And from volumetric flow rate, we can divide it with area of nozzle Q over A, and then we get the velocity at nozzle exit U1. Using U1, we can calculate the velocity at impact with vane or bucket. U null or U0 equals to this equation right here. And last but not least, using the mass flow rate divided by velocity at impact, which is m dot divided by U null or U0, we can get the momentum flow in jet at impact J. And F1, which is the force on vane or bucket, as I have explained earlier, is this equation right here. Okay, so after you have calculated all the value for F and J, you can actually plot a graph of F against J, and the graph will actually look almost like this. Okay, so the slope for hemispherical cup should be 2, while the slope for flat plate surface should be 1. Okay, but if the value for the slope is less than what it should be, then that means that in the experiment there are some errors that affect your data and your efficiency, so that's why the value is not the same. So that's all from me. I hope that this input will be useful for you to understand the description of problem better later on. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Akmal Haziq, and today I'm going to present about the problem statement. We choose control volume lab experiment from subject fluid mechanics. It is an engineering problem as this experiment is applicable in the future as engineer. For example, Pelton wheel, as my friend said earlier. And some real life engineering problems will apply this experiment too. Yes, the scale might be bigger. So the program should be applicable not only to this lab experiment but also in the future. Now, what do we already know? We know the objective of the experiment, which is to find the value of F and J and to find its relationship. And we know that user already have quantity, time, and displacement of weight jockey. Now, we also know the formula to find the 5 desired parameters. And the problem that we found is that user has to calculate 5 parameters for 14 times minimum, and it is tiring. And user might want to repair the data and repeat the calculation. So it's not just 14 times, but maybe more, because maybe if there are some error in the text file, so maybe user want to edit it, or maybe user want to run the experiment for many times, so user want to get more accurate data. So to calculate 5 parameters for a lot of time, it is very tiring. Now, what do we need to know? We need to find the value of force, momentum, and mass flow rate, velocity at impact with vane, and velocity at nozzle exit. And this is one of the objective. And the other objective is to know the gradient, to know the relationship between F and J. And then we need to know if there is any error of the experiment, and we need to know if user want to repeat the calculation. But why do we need to know it? you need to know to accomplish the purpose of the experiment. And if user can know if there is any error earlier, user can fix the setup before proceeding. So basically user can get more accurate data if user know there are some errors in the text file, and let's say user accidentally keyed in wrong data. So user can know without spending much time doing useless calculation. And once user get the desired output, user can interpret the data. So user can repeat the experiment as many times as user want, as it's very convenient and easy to use, because user just need to key in 3 data and user can get the output as soon as possible, which is very easy. But how do we find it? We make a program that helps to calculate the desired parameters, and we can get the parameters only by inserting measured data in a text file. And the program should also be able to calculate the gradient to show the relationship between f and g. And theoretically, relationship between f and g should be directly proportional, and the value of the gradient should be 1 or 2 depending on the surface, whether it's flat or hemispherical. And the program should also be able to tell if there is any error in the experiment so the user can fix it. And the program should be flexible if the user want to repeat the calculation upon repairing the data. So if user key in wrong data, wrong numbers, wrong values, so user can always fix the data and redo the calculation with no time. So which is very convenient and easy. And that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ukail. I'll be explaining about the technicalities and the structure of the program. So without further ado, we move on to the program. So here is the first part. The first part is, of course, here is the declaring variables. We're going to be using an array with a size of 7 for 7 trials. So array, as we all know, that array can store many data, like according to the sizes that we have set. So for this, we set for size of 7, so it can store for 7 spaces or 7 trials in this case. So moving on, here is the input, the prompt input from user, the welcome blah blah blah, choose either A or B. So if the user chooses A, it's going to be a flat surface. If it is B, it's about hemispherical. Here is the table displaying later. If you are curious, there's a snippet above for an example. It's very small, but we'll get into that later by another member. So here is the conditions. So there are 2 options, either A or B. When the user chooses A, it's going to be calculating the flat. If it is B, it will be using the hemispherical. So it will open different text files. So blah blah blah. Moving on, proceed to the calculation part. So here is the key part in this program. So for the calculations, we'll be calculating first is the m dot. M dot is the mass flow rate. So the formula for m dot is QTY. QTY is the water, the mass of water collected divided by time. So after we got the m dot or mass flow rate, we'll be calculating the U1. U1 is the velocity at the nozzle. So using this formula, next we'll be calculating the total J. Total J, which is the moment. We'll be calculating the momentum flow in a jet at impact. So here is the key part here. Yes, we'll be finding total J. So for the momentum itself, momentum J, the formula is m dot times by U naught or U0. So moving on, we need to calculate the total force, or the force, total force on the plate. So for the total force, the formula is here. Use this and we get the force, and then for the total force, total F plus force I. then we'll be having our total force on the plate, which is F. Now here is how to calculate the gradient. We need to also calculate the gradient in this program. So formula for gradient is, of course, is in integers, total F over total J. Total J, the momentum. Moving on, so here is where we are to be replacing the values from the old text files into the new ones, data flat new. So this is going to be the new text files that will be created later on. So if it is the user inputted A earlier, so it will be data flat new. However, if the user inputted B, the new data will be stored in data hemispherical view. Remember, the A is for flat, B is for hemispherical. These are the final messages of the program. It will, if it is and there is an error, the error conditions are only if for A, for option A, which is flat, if the gradient is not equals to 1, there will be error. If it is 1, then there is no error. If for option B, if the gradient is 2, no error there. If it is not 2, then there will be error. Next, the program will prompt the user whether to run another or whether to exit the program. So yes, that is all. And then if the user input yes to run another time, the program will repeat itself. If the user inputted no, not to run another time, then it will end here, and the user will get an output. So that is all.
Assalamualaikum warahmatullahi wabarakatuh, and a very good day. My name is Siti Nurfatehah binti Sapuan with ID number 1-800-2250. So for this part of the presentation, we're going to talk about text file processing. So let's see our program. In our program, we already include the fstream library and declare the if stream in file because we want to read the text file. So which location are we referring to? These two. It's at the same location of new volume D, second year 5th semester file, SPDB file, and here they are, CV data flat and CV data hemispherical of A and B. To proceed, let's see if our program works by clicking on F11. Alright, here is our program. In our program, we either have to choose A or B. So at first, let's choose A, of flat surface. Let's open file of CV data flat and compare it with our program. You can see all of the data over here of QTY, time, and Y are the same with what inputted in CV data flat previously. So for the rest of the data, including the prior data, will be stored in CV data flat new. You may compare with the current one over here. They are exactly the same. But where in the program did we declare that? We declare that over here, off stream out file for this one, for CV data flat new. But what if suddenly, after going through all of this data, suddenly the control volume engineers undergo the other experiment of manipulating the rest of the data? Here, let's open CV data flat, and suddenly they are changing few of the data by changing them to 32 as an example, and 67 over here. Save. Alright, so here choose yes because you want to proceed, and choose A again. Here CV data flat, you may compare with them that they are of the same number that the latest input, 67, and they will be restored in the CV data flat new. The newest data will replace the previous data in the CV data flat new. So if they want to refer to their previous data, they may refer to the screen of their calculation program. So let's see if it works for CV data hemispherical, choosing yes, and choosing B. Alright, so let's compare with CV data hemispherical. See, they are of the same. So, what about the new? Yep, exactly the same. So let's proceed, and we are manipulating CV data hemispherical data by changing few of them to 32, 187 saved. Alright, so choosing B again. So let's compare with our latest data input. Here we already input new number 187 here, 32 here. So let's see if it works for CV data hemispherical new. Yep, they are exactly identical. So our program are proven to work. The significance of our program is that for their own personal references, they may refer to their calculation screen to refer to their previous data, and to lessen the hassle of reviewing so many data, the latest data input in their CV data flat or CV data hemispherical will replace the previous data calculated for CV data flat new and CV data hemispherical new. So that's all. Thank you.